Okay, so we're going to look at, suppose I've got a circle, and in the past you had a geometry problem whereby you were given, say, the measure theta here, the central angle of a circle, and you were asked to find, say, the area of this sector in here. And your strategy was, say, okay, well, that's a portion of the whole circle. It's like a slice of pizza. What portion of the whole circle is it? Well, it's theta, if theta is measured in degrees. It's theta 3/60ths of the area of the circle of pi r squared. So there is the length or the area of that sector in there. Associated with that sector also there's an arc. We have this arc right here. And that arc is a portion of the whole circle's circumference. So what would the length of that arc be? It would be theta 3/60ths of 2 pi r. Oh, theta 3/60ths of the circumference. That's if I'm measuring in degrees. So let's say we're going to do the same thing now in radians. We still have the same setup. We've got central angle in the circle, measured now in radians, theta radians. I've got a radius. I've got this arc length out here, which I'm going to call S. And remember, this angle I could consider to have been in standard position, in which case I've got my angle theta standard position, and we called this before our definition of radian measure. That arc length out there we called S. Whether the circle had a radius of 1 or whether the circle had radius whatever, we'll call that arc length S. So if I set up this picture and think about it in terms of radians, I want to know what portion of the circle is, of the circle's area is the area of the sector. Well, it's going to be whatever proportion the arc length is to the whole circumference. And the whole circumference of the circle in this case is 2 pi r, and that arc length is S, so I have S 2 pi r's of the area of the whole circle, which is pi r squared. So in terms of finding the length or the area of that sector, I'm S 2 pi r's of pi r squared. There's no radian measure in there. I do remember that theta is going to be, by definition, S over r. And that's my definition of radian measure. Therefore, S equals r times theta. What I then can do is substitute that value in for S. Let's make this a little smaller here for a minute. And then what I'm going to do is get S over 2 pi r times pi r squared, make that substitution in, so I then am going to get 1 over half, and let's see, S goes in, r theta over 2 pi r times pi r squared. And then let's simplify. The r's are going to cancel, my pi's are going to cancel, and I'm down to the area equals 1/2 r times S. Again, still have no theta in there, so I could write the area of that sector in terms of the product of the length of the radius and the length of the arc of the circle. And that's pretty cool. Area of a sector is 1/2 rs. Now, if I want to, I can keep the theta in there as well. We have that theta equals S over r. So if I go ahead and just leave that alone as is, it's going to be equal 1/2 theta r squared. So either of those two formulas is going to be good to find the area of the sector of a circle. One of the two formulas, again, is in terms of lengths, and the other formula is in terms of the radius and the measurement of the angle in radians. What's important with this formula, that measurement is a radian measure, not a degree measure, a radian measure. So let's, another application of radian measure here is something that's called apparent size. Let's suppose I'm standing on Earth and I look out and I see a planet out here or the moon or something. I am a very great distance away from that object. And if I eyeball it and hold it up, I could actually talk about measuring the angle from, say, the top, the bottom of the object that I'm seeing to the top. And I might want to know something about the relationship among the angle, the distance that I am to that object, and say the diameter of the object. And there are two keys to what's called apparent size. One key is apparent size is the measure either in degrees and radians of this angle. So apparent size is an angle measurement, one. And number two, the idea, again, which is going to come up in calculus a fair amount, is that if I were to imagine this angle to be in standard position, there's going to be some circle that's going to go through here. And if I'm looking at my object out here, a very tiny angle measurement, the straight length segment, say the diameter of my planet, is going to be approximately equal to in length to the arc of that circle. And that's the key for apparent size. We're going to say that if we want to approximate the diameter of the planet, we can just go ahead and use the length of the arc of the circle. And again, local linearization is not a difficult concept. If I have a circle and I hone in on a little tiny section of the arc, it's going to appear locally very straight. It's not going to appear very curved at all. It's certainly standing on the Earth's surface. We know the Earth is a sphere, but we stand on the surface and it appears pretty flat for us over local short distances. So apparent size, again, is the measurement of this angle. And those are the two key things to remember for apparent size.